Hi everyone, I hope you're ready for chemistry, because, it's fun and stuff. So, in this video, I'll hopefully be explaining the trends in the melting and boiling points of elements in the periodic table for you. Okay, so this is a periodic table I found on the internet. It's really cool, and I'll show you. If you didn't already know, well, this is a periodic table. Okay, so the periodic table is split into three groups: metalloids, which are these ones here. And then you've got the non-metals, and then you've got the metals. Simple, right? And then with the two groups, non-metals and metals, there are subgroups in them. So with the non-metals, you've got the other non-metals, the halogens, and the noble gases. And then in the metals, you've got post-transition metals, transition metals, lanthanoids, actinoids, alkaline earth metals, and alkali metals. Okay, so the periodic table is split into those three groups based on their bond type. For instance, elements in the non-metal group show covalent bonding, while metals present a metallic bond. And on the left is the covalent bond, and then on the right is the metallic bond. But metalloids are different because they have properties of both a metal and a non-metal, so they can't just be put into one group. Okay, so as a rule of thumb, non-metals have low melting points and boiling points, and metals have high melting points and boiling points. So the easiest way to look at the trends for melting and boiling points is to break it down into smaller groups. So with the metals, group 1 alkali metals, you've got the melting point decreasing as you go down the group. So that means lithium would have the highest melting and boiling point, and francium would have the lowest melting and boiling point. Okay, so to understand why this is, you need to know a few things about atomic radii, atomic structure, and how melting and boiling works. So the first one, melting and boiling occurs when the bonds in the element must be broken. Okay, and what's used to break the bonds is energy. So like in a solid, the atoms are all close together, so it takes a lot of energy to like break them apart. And for the purpose of this, the energy that we're using is like heat. So when you go down the periodic table, the amount of protons and neutrons and electrons increase in the element's atomic structure. So remember before we talked about metallic and covalent bonds, and as we know, group 1 alkali metals have metallic bonds. So the strength of metallic bond comes from the attraction between the nucleus, which are the protons and neutrons, and then the electrons around it, or which are also known as delocalized electrons. So as you travel down the group, the atoms become larger, so the distance between the nucleus and the electrons increases. So it's like, oh, I'm here, and then like I'm all the way out here for like francium, but then, oh, I'm here, and I'm so close to you for lithium. So as you travel down the group, the atoms become larger. Yep, so that means the attraction is weaker. So if you were following what I was saying before, you can get that when you go down the group 1 alkali metals, where the atomic radii gets larger, so the bonds are weaker. So that means less energy, in this case heat, is needed to melt and then boil the element. This shows how the element's melting and boiling point is inversely proportional to the atomic radii. So with non-metals, the trend is different compared to the metals. Instead of the melting and boiling point decreasing as you travel down the group, they increase as you go down the group. So it's like, so there are a number of reasons for this one. Atomic radii and van der Waals forces. To first understand van der Waals forces, you have to understand that non-metal molecules have intermolecular attraction. So that means there are attractions between two nearby molecules. So it's like, so we know that electrons are always moving, right? So that means for even just a tiny bit of time, one side will have more electrons than the others, making one side more negative and one side more positive. When an atom that's charged comes close to another atom that's not charged, it'll like induce a charge on it, making an intermolecular attraction with the two atoms. So it's like, oh, I'm negative, I'll just make this one negative, because I'm cool like that. So yeah. So why are van der Waals forces so important for this? That's because they relate to the atomic radii. With non-metals, the larger the atomic radii, the stronger the intermolecular attraction. This is because, as we talked about in the metals part, there are more electrons, meaning more induced charges, which equals a stronger attraction. So with a stronger attraction, this means that it just has a stronger bond, and it takes more energy to break it apart, meaning you need a higher temperature to melt and boil the element. For transition metals, the melting and boiling point increases as you move from the left going to the right of the table. Then once reaching its peak, it decreases. except with technetium and manganese, which are in period 5 and 4 respectively, they're an exception, and it should be noted that they're both in group 7, so group 7 going down, but you know, like that. Tin is also an exception, as it has a higher melting and boiling point than you would think. Last but not least, you've got the period 2 and 3 non-metals, excluding carbon because, well, when I want diamonds, it doesn't give me any, so I don't really like it. Period 2 and 3 non-metals are similar to transition metals, except it doesn't peak and then go down. It just has its highest melting point, and then it just goes down gradually. So like nitrogen, and then it goes down to neon. It's the same with phosphorus, having a higher melting point than argon. So yeah, again we're excluding sulfur because it's really smelly. So from the non-metals we can see when you go across the periods, the highest melting point here, and then as you go down, the lowest melting point is there. Okay? Conclusion, with metals, as you go down, the melting point decreases, and with non-metals, the melting point increases as you go down. Then with transition metals, it moves in, and that's about it. I hope that all makes sense to you, and if it doesn't, you can always look at breads. Hey guys, sorry for such a long video. I didn't expect it to be like 6 minutes long, except, well, I talk a lot. No, okay, it's more than 6 minutes now, but yeah, thanks for watching. I hope you got that all. If you don't, you can just look down and read what I said, because that's basically what I said. So I hope you enjoyed it, and if you actually watch the whole video, there's a secret message. So if you see it, write it down in the comments, and I'll give you a chocolate. Thank you. Bye.